Hello, this is our project for the Statistics of Engineering, and it is about Beijing air quality analysis. Our team has four members: Abdurrahman Jawad, Alan Kazakov, Majid Javada, and Ziaprizadeh or me. Now let's start. We're gonna start with the statistical analysis of air quality. This presentation summarizes details analysis of urban air quality in Beijing, China, using data collected from the AOT's A2 Zhangxing monitoring station between 2013 and 2017. This project explores how environmental and meteorological factors influence ozone concentrations with the supporting air quality management and public health strategies. Our objectives and goals are to clean and analyze the sample of air quality data, understand the distribution and variability of key pollutants and meteorological variables, assess monthly trends, examine intervariable relationships, and develop predictive models for ozone concentration. Both parametrics and non-parametrics methods were used for robustness. The data itself is originated from the Beijing multi-site air quality dataset and consists of hourly records over 5 years. A sample of 200 daily observations was selected from the A2 Zhangxing station. Variables include ozone, SO2, NO2, CO, wind, and temperature. This manageable changeable retains enough variability to support comprehensive analysis.
Okay, moving on to the descriptive statistics. It revealed that the ozone and the other pollutants had very high variability. For example, the ozone values range from 0.2 to 423 micrograms per cube meter, with a coefficient of variation over 100%. This indicates significant daily fluctuations. Temperature ranged from minus 16.8 Celsius to 40.5 Celsius, reflecting the multi-season scope of our data. Distribution of ozone concentration. Ozone levels followed a positively skewed distribution, with over half of the data concentrated in the 0 to 50 microgram per cube meter range. A long right tail suggests the presence of sporadic extreme pollution episodes, particularly in the summer months. These characteristics have implications for public health and statistics modeling. This graph shows how skewed the graph is, where more than 50% of the data is between 0 and 50 micrograms per cube meter. And the long right tail suggests that there's very high variability and it goes to a very high number. Normality and variability. Normality tests using the Shapiro-Wilk method indicated that none of the 6 variables followed the normal distribution at a 5% significance level. This required the use of non-parametric alternatives. High coefficients of variation, especially the sulfur and the carbon monoxide, confirmed the presence of substantial relative dispersion. Let's talk about the hypothesis testing results. A one-sample t-test showed that the mean ozone level significantly exceeded the WHO guideline at 40 micrograms per cube meter. An ANOVA test revealed that ozone levels varied significantly by month, with peak concentrations observed in July and May. Post-hoc analysis confirmed these seasonal patterns were statistically robust.
Here we can see some plots, specifically 2 of them. One of them is the box plot about the ozone levels by month, and the other one is the 95% family-wise confidence interval. So let's talk about correlations between variables. Pearson correlation analysis highlighted key associations. Ozone had a strong positive correlation with temperature and a strong negative correlation with NO2. These findings suggest that high temperatures facilitate ozone formation, while NO2 might act as a limiting factor or a chemical sink in the atmosphere. We also constructed a correlation matrix, and over here we can see that there is a strong correlation between the NO2 and the CO, as well as a correlation between the ozone and the temperature. There's also a relative correlation, we can say, between the ozone, NO2, and the wind. And the ozone prediction model, we also built a linear regression model to predict ozone levels using 5 environmental variables. The model explained nearly 60% of the variance. Temperature and NO2 were the most influential predictors, with temperature showing a strong positive effect and NO2 a strong negative effect. Here we can see 4 different plots, to be specific: residuals versus fitted, scale location, and residuals versus leverage. But I want to make a specific point about the key residual plot, which essentially tells us that on the boundaries, specifically for the -2 and the 1 theoretical quantiles, we can see that the data follows a nonlinear pattern. Here's when the predictions of the linear regression model may become unreasonable and unexplained correctly.
Hello, this is Majd. So by grouping ozone and temperature levels, we identified a clear link or relation between the high ozone and hot days using the chi-square test. A cross-cal voice test confirmed monthly ozone variation. This reinforces insights from parametric methods. So basically, ozone pollution in Beijing is episodic and driven by temperature, often surpasses health limits in summer. In contrast, we have nitrogen dioxide that shows a complex but opposite trend. These findings highlight the need for adaptive air quality strategies that reflect seasonal and environmental shifts. Thank you. So talking about future work and recommendations, future work should use complete data sets, integrate real-time forecasting, and add spatial analysis. Targeting pollution by season and using temperature-based alerts can strengthen public health and mitigation efforts.